Hi folks, in this video, I'm going to show you how to perform a one-way independent groups ANOVA using JASP. First open up JASP. Once JASP opens, go to Show Main Menu, Open, Data Library, ANOVA. We're going to go ahead and select the Facebook Friends file since that states that it demonstrates use of a one-way ANOVA. When the file opens, we want to become familiar with the data set. We can see that the participant number represents the participant number. The friends is the experimental group, which represents the number of friends, or the number indicates the number of friends accounted for in the mockup profile. And the score represents social attractiveness, a dependent variable where 1 is the lowest rating and 7 is the highest rating. To go ahead and perform the ANOVA, we're going to go to the top and select ANOVA, and we're going to choose ANOVA. Once the dialog box opens, we're going to take the score and move that to the dependent variables box, since that's our dependent variable. We'll select the friends and move that to the fixed factors box, since that's our independent variable. Before moving forward, we'll select descriptive statistics and we'll check for our assumptions. Remember, we want homogeneity of the variance assumptions. If the ANOVA is significant, we'll also want to check for post hocs. Go ahead and select post hocs and move the independent variable of friends over to the post hoc box and select the kind of post hoc you want to perform. We'll go ahead and perform Bonferroni, since that's what we learned in class. If we take a look at the output, you can see that if we took a look at the descriptive statistics, we have different levels of the independent variable. In this case, we have 1, 2, 3, 4, 5 levels or 5 groups. So descriptive statistics provide us similar information that we've known all term. To check for the basic assumption of homogeneity of the variance, we'll go ahead and look at the Levene's test for equality of group variance. If we look at the p-value, we see that it's smaller than 0.05. So this is a violation to the basic assumption of equality of group variances, which means that the variance of some groups for the dependent variable of interest are not homogeneous compared to other groups for that same dependent variable. So this is a problem. For all intents and purposes, though, we'll continue to move forward to show you how to perform this analysis. So next thing we want to look at is the ANOVA. And you can see that ANOVA is based off of the sum of squares, the degrees of freedom, the mean square, the F, and the P. It's easy to jump right to the P because you see it's statistically significant. But let's make sure you understand what each one of these rows represents. In class, we talked about how there's something called sum of squares between and sum of squares within. And what we said is that the sum of squares between represented the explained amount of variability in the dependent variable that was attributed to group membership. So here, our independent variable of friends represents that value, sum of squares between. So the sum of squares between groups that is accounted for in the independent variable was 19.890. To determine the degrees of freedom, remember, we use k minus 1. And so because I have 5 groups minus 1 degree of freedom, my degrees of freedom in this case would be 4. If I took the sum of squares of 19.890 and divided it by its degrees of freedom, we would get the mean square of 4.973. Similarly, for the sum of squares within, or the residuals, or the error, that which is not explained by the independent variable, we have 154.867. divided by its degrees of freedom, which, remember, the denominator is determined by taking n, total sample size, minus k, number of predictors. And so if you took the total sample and minused it by 5 levels of those independent variable levels, you would get 129 as degrees of freedom. If you took the sum of squares for the residuals and you divided it by its degrees of freedom, you would get the mean square of 1.201. To find the F statistic, you would take the mean square between value, 4.973, and divide it by the mean square residual or within of 1.201, and you would get an F statistic of 4.142. That's our F observed that we're going to compare to the F critical value. If you compare the F observed to the F critical value, which we showed in a different video, you can see that the p-value is smaller than 0.05. So this tells us there's a statistically significant difference somewhere in the social attractiveness score, that dependent variable of interest, between these 5 groups. But the problem with ANOVA is it doesn't actually tell us where that significance difference lies. So we got to run post-hocs. If we scroll down to our post-hocs, you can see the p-value, which is Bonferroni corrected, and all the values here. Any value that is smaller than 0.05 tells us that there is a significant mean difference between those two means themselves. So here you can see people who have 102 friends compared to people who have 302 friends, there's a statistically significant difference at that level. Similarly, you can see that people who have 302 friends compared to people who have 902 friends, that there's a statistically significant difference between those means. And so none of the other means are actually significant. So that's helpful. So while the ANOVA is statistically significant, it's the post-hocs that are going to tell us where those group mean differences lie. And we can see that that's the case, right? So if you look at the mean and the standard deviation for 102, you can see that the value is 3.817. And if you look at the value for 302, you can see that it's 4.879. And so what that means is that on the post-hoc, that the social attractiveness score of 3.817 is statistically far enough away from 4.879 at the 0.05 level, which remember is with 95% confidence that we did not make a type 1 error. So I hope this video is helpful. We'll see you all in the next one.